So until very recently, maybe at most 15 years, the only way to get the quantitative data on the atomic structure was from scattering. And about the year 2010, so actually not that long ago, it has been shown that the progress in electron microscopy allows us to get the fairly precise numbers about the lattice parameters, atomic positions, and so on and so forth. So the question becomes that now that we have the electron microscopy that becomes quantitative, can we somehow use it to get the information about the physics and chemistry of materials? And the question is, what is that we're going to look at? So what matters? So with the modern STEM, if we are careful about the data acquisition and about the data quantification, we can determine the positions of the atomic column down to the picometer. So maybe a plus minus, but kind of on that level. So what can we learn from the atomic positions? Very straightforward. For example, if we have the carbon-carbon bond, depending on the bond lengths, we can say whether this is a single bond or double bond or triple bond. So the whether it is double or triple directly relates to the chemical activity of this bond. If we deal with the, let's say, oxides, then the angle between metal, oxygen, metal determines whether this material is metallic or isolating, or it determines whether it is magnetic or non-magnetic. So in fact, for starting from about 60s when John Goodenough and Kanamori worked on the development of the Goodenough-Kanamori rules, people knew the relationship between magnetism, conductivity, bond angles, and bond lengths. So the other things like tetragonality, if the material goes from the ferroelectric to non-ferroelectric phase, the unit cell stops, let's say, stop being tetragonal and becomes cubic. It used to be the case that all of these parameters could be learned only from scattering. But with the high-resolution electron microscopy, we now can determine this type of characteristics in real space. And more importantly, we don't necessarily need to have the whole material as ideal single crystal. So for example, if we start to measure the bond lengths or the bond angles, and we have some form of the extended defects or surface or the grain boundary or dislocation, we can see how these parameters start to evolve from the almost ideal bulk close to some microscopic defect. So if you think about it from the point of view of the insight it gives us into the physics and chemistry of material, this is actually kind of super important. And another very important thing about this type of analysis is the chemistry effects. For example, if we look at the oxide material in the electron microscope, we can see the oxygen columns, but we don't necessarily see individual oxygen vacancies. So if some oxygen is missing, we are not going to see it directly. But what's interesting is that many materials have a very strong coupling between the unit cell volume and the oxygen non-stoichiometry. So this is called the Weger strain. So if we start to pull oxygen out of the materials start to expand. So you can think about it that the cations are kind of glued by the oxygen between them. If you pull the oxygen out, then the cations are glued to the small extent. And these chemical strains are actually pretty large. So many of you know that batteries can expand and contract when we operate it. So fuel cells sometimes are difficult to control because they can crack because of this chemical expansion. Well, the great thing is that if we can measure 1 part out of 100 or 1 part out of 200 for the atomic spacing, we can basically use this chemical strain measured directly on the atomic level as the measure of the concentration of vacancies inside the materials. It's actually super cool. So this being said, nothing is for free. So whenever we have any type of imaging system, the data that we get on our detectors is the convolution of what happens inside the material and the properties of the measurement system. For X-rays, we know how to calibrate X-ray systems very well. So we kind of take the X-ray data and we believe that the X-ray spectrum is representative of material, and our measurement system has already been taken care of, so we calibrated for it. For electron microscopy, as you observed in the first part of the tutorial today, the way that image looks like subtly depends on a lot of things like slight misorientation, focus, and so on and so forth. So the first and very important thing is that if we want to analyze the electron microscopy data to get this type of physical descriptors, we need to be very quantitative about how we tune our system, about how we remove the effects of the mist tilt, and so on and so forth. So I'm not going to talk about it because Gerd has already talked about it, but the general principle that garbage in, garbage out works in all cases. So if we want to be able to learn physics from observational data, we need to make sure that the data is corrected for the instrumental factors. More importantly, we know that not all instrumental factors can be corrected for precisely, so very often it requires some form of calibration. In this case, it's a very good idea to understand the physics of the image formation mechanism in electron microscopy, because that in turn can tell you what type of physical observations you can trust and what type of physical observations you cannot trust. For example, if you have the mist tilt effect, it basically means that one part of the image is tilted slightly differently than the other part, but you can expect that the mist tilt will create some form of smooth gradients within the image. And if you start to see something that has a periodicity of double the unit cell, then that's not a mist tilt effect. It cannot be. So the next question becomes is, how do we interpret this physics? Because generally, if I tell you the information about the coordinates of all the atoms in the solid, it's absolutely not equivalent of understanding what actually goes on, because being able to read all the letters, that is not equivalent to understanding the story that is in the text, right? So for the time being, this field is still being developed. However, one of the earliest tangents of thinking in this field was trying to take the STEM data and map it on the physical order parameters that we understand very well. Things like polarization, octahedral tilts, strains. So these are the things that people study macroscopically. And now the idea is that we can observe them on the atomic scale. So how can we do that? And this is the case where you know, the first time I saw the papers coming out of GEA group in 2009, 2010, my question was like, okay, I didn't realize that we can do it this way. Because it turns out that if you want to analyze the physical order parameter fields out of the high quality STEM data, what you can do is just take the image, fit the position of each column by a certain function like a Gaussian, take the position of the center of this Gaussian and say that this center of the Gaussian is just the position of the atoms. As simple as that. And then for many things like order parameter fields, for example, for polarization, you can simply find the high intensity columns, find the geometric center, kind of the cross-section of the diagonals, and then you can see to which extent the central atom is off from the position of this geometric center. So the fact that this was possible was absolutely astounding, because typically people think about polarization mapping having a big crystal, doing the X-ray measurements, what's not, and all of a sudden you can just physically measure the displacement of the atom compared to the high symmetry position. And the way that this type of data analysis can be done is very straightforward. You take images, you find the position of each atom, you find the displacement of the central atom compared to the cross-section of the diagonals, and then you get a vector field, and then you can just map this vector field, and you basically get a beautiful, pretty much atomically resolved maps of how the polarization field is distributed inside the solids. And then you can start to see very interesting things. For example, this is the ferroelectric domain. Polarization goes this way and this way. And you can interestingly see that this type of domain wall is going all the way to the interface. And this type of domain wall actually forms the counter domain. So it almost forms like a ferroelectric vortex at the interface. And there are very good reasons as to why it happens and what type of information you can learn about the material from these observations. But that was super impressive because this is really when people start to get the atomic level insight on what happens inside this type of materials. So this is kind of another example of the same type of material. The polarization distributions are sometimes can be more complex than just the domains. So in several materials, if you balance, grow the material when you have the non-ferroelectric part and the ferroelectric part, polarization will actually self-organize into the vortices. And the reason why it does it is because polarization doesn't want to stop. It kind of forms depolarization charge. The way to compensate the depolarization charge is to make the polarization rotate. And for the right ratio of the thickness of the layer and the depolarization screening, it can actually translate into these vortex structures. And these have been discovered in 2016, so almost exactly 10 years ago, but they're still being studied even now. So one of the recent Nature Materials paper was the discovery of the ultra-high dielectric properties in this type of structure, because these vortices can respond very easily to out-of-the-plane fields. But again, this is something that you can see by the electron microscope. It would be virtually impossible to discover them using the X-ray scattering because they're fairly large and they're fairly disordered, which means that on the X-ray scattering, they give rise to some pretty high noise background. It turns out that we are not limited to polarization only. So we can also map the octahedral tilts. So sometimes the ferroelectric materials, or generally perovskites, distort by co-rotation of oxygen octahedra. And it turns out this also can be visualized directly in the image plane. You just see how the octahedra rotate. So interestingly, we generally think about the electron microscope as the tool that gives an excellent resolution in XY plane. So we look in projection, but relatively poor resolution in Z plane. So it turns out that if the octahedra rotate, to some extent, we can also resolve the tilts into the Z direction because the atomic columns kind of start to double. So if they were going like this inside, and then they start to tilt, then the atoms kind of elongate because you sort of look at their projection, and you can determine what type of tilting it is based on the atomic column shape. This being said, we definitely can map this physical order parameters. This map is partial because we can map in-plane components, but not the Z component very well. But the next question becomes, what can we learn from that? And that's a complicated problem, and that's the problem that appears all the time in the context of electron microscopy, that at some point we need to make a transition from observation when we get a lot of data to building some sort of physical model. Just having a lot of data, if we don't understand what it means and how to generalize it, it's almost useless. What we need is to understand what's the physics of the material. And for that, we need to have some physical model which is consistent with what we know about these materials, but this model can also be informed by the observations. So for most ferroelectric or ferroelastic materials, we typically work with the concept of the order parameter. So tilt is one order parameter, polarization is another order parameter. So basically what the order parameter means is that imagine that you have solid. There are 10 to the power 23 unit cells in the macroscopic chunk of it. So that's a Avogadro number. So what the order parameter means is that all these unit cells transform in lockstep. So they behave almost indistinguishably. So it's what is called the collective variable. And traditionally, we study these order parameters by scattering on average, but two things. So we can study only bulk phenomena by scattering, but we don't know what happens at surfaces. We don't have know what happens in the interfaces. And we also that there are materials where the concept of the order parameter doesn't work very well. For example, if you heard about things like spin glasses or spin liquids or relaxed ferroelectrics or morphotropic phase boundaries, these are the systems where it is not clear whether this collective variable exists. And as often happens, these are also the materials that have some super interesting properties. For example, materials with relaxed ferroelectrics have the ultra-high dielectric constants, which means that people love them for applications, but we just have no clue what happens with these materials on the atomic level. And another problem is that if we describe the materials by the order parameter concept, meaning the mesoscopic field that contains all the relevant information, there is a fundamental physical fact that we need to know the boundary conditions for this field. So what happens on the interfaces? If we know what happens on the boundary conditions, we can predict what follows inside. But we don't have any way to determine the boundary conditions from the mesoscopic data. It needs either to be speculated, or we need to have some different information sources. Then there is a third thing which kind of matters a lot, is that whenever we deal with the experiments, we always deal with, have to take into account what is called the unknown or latent variables. So for those of you who are from elder generation, there was a Minister of Defense for US, Donald Rumsfeld, who very famously said that there are things that we know that we know. There are things that we know that we don't know, but we kind of know where to look for. And then the really dangerous things are the ones that we don't know that we don't know. Obviously, Donald Rumsfeld was not the first one who came up with this concept. I think the original statement to this effect goes to Adin Tousi about 800 years ago. But obviously, he was talking about donkeys rather than knowns and unknowns. But the idea is actually exactly the same. So the question becomes, is that when we deal with the experimental systems and the real materials, we very often have unknown unknowns. And they can generally be generalized, or we have a surface damage. For example, imagine that you take a sample and put it in the electron microscope, right? The sample was made by FIB. Why would you even think that the surface of the sample would be simply the cut of the ideal material and not contain some sort of disorder? Doesn't follow from anything. So in my case, I worked on scanning probe microscopy almost exclusively until 2015. And then I realized that if I want to use machine learning for microscopy, it's much better to start with the field of electron microscopy, because atom is an atom. Scanning probe microscopy has a lot of external control factors. For example, if I do some sort of measurement on the surface, I get some spectrum. If I breathe on the surface and I do the same measurement, I will take a totally different spectrum. Both are reproducible, but are clearly affected by the factors which are not material specific, meaning me breathing on the surface. My assumption was that if you work in the electron microscopy, what you see is what you get. An atom is an atom. That actually turns out absolutely not true, because if you spend considerable amount of time of STEM, you also see the atom growing, appearing out of nowhere, moving around, and so on and so forth. So unfortunately, by the time when I figured it out, it was already too late to say that I don't want to do it anymore. So it turns out, however, that in many cases, microscopy allows us to visualize these unknowns. For example, if we look at the bismuth ferrite surface, you can immediately see that the surface of the material has a considerably significant expansion and reduction of the intensity of the atomic columns compared to the bulk. So something happened. We don't know exactly what it is, because that was done at the time when we did not have the EDX capability, but we can speculate that there was some partial removal of the oxygen atoms as the result of the interaction with the atmosphere. We also know, so this is, in science, there are a lot of things where you get evidence from different sources that together does not form a proof, but jointly they kind of combine to the same view of what happens in the world. So I also know that for the same material imaged by a very different technique, meaning the AFM, I can see the, under application of certain bias, I will see the surface slightly expand, and this tunneling current will change completely. So I cannot say that this mechanism and that mechanism are the same, but I do know that these surfaces of these materials have a proclivity for changing chemical composition on the atomic level. And the great thing about STEM that it can be detected. So there are other things that we can do. So this is the example of the octahedral rotation, so close to the surface or sample surface. So notice what happens in this case. So we know that material, this is how the tilts in the system evolve. We can directly measure these angles, and you can see that the tilts start to disappear somewhere between about 5 unit cells away from the surface. So this is not an atomistic effect. This is something related to either induced by chemistry, or this is some form of the correlation lag. So we don't know what it is, but at least we can measure it. We can do even more interesting things. So imagine that this is the interface between the lantern strontium manganide and bismuth ferrite. So this material is the, both of them are perovskites, therefore they form a coherent interface. This material is ferroelectric, meaning it has polarization. This material is not ferroelectric, therefore it doesn't have polarization. So look what happens if we start to measure the lattice expansion, so lattice parameter, and the displacement of the central atom. So this is a measure of the polarization. This is the measure of the lattice parameter. So the lattice parameter goes like this. So this is the bulk in one material. This is the bulk in another material. And then for whatever reason, at the interface, the lattice seems to be expanded compared to the both end members. If you look at the polarization, it goes like this. So here polarization is 0, so LSMO is not a ferroelectric material. Then here polarization is positive. You would expect that if you have material where polarization is 0 and positive, that in the interface there would be some gradual transition. We just don't know how sharp this transition should be, but that's not what's happening. Look what goes on. So in this case, you can see that polarization first goes down and then it goes up. And interestingly, that this correlates with this lattice expansion. But if we take the material that has the polarization in the opposite direction, so notice that this is also LSMO BF4, but in this case, polarization is towards the interface and not away from the interface. Notice that the behavior is totally different. So in this case, polarization is 0 here, polarization is negative here, then it goes down a little bit, but we don't really have this anomaly with the polarization going in the opposite direction, and we don't have the change of the lattice parameter. So if we combine this sets of information and represent it slightly differently, so this is what we have. This is LSMO BF4, positive polarization, negative polarization. Notice that if the polarization is negative, it's 0 in one component, goes down, there is a jump, and then it is constant. In this case, it's constant. Then for whatever reason goes down, then it jumps, and then it gradually increases. So if you look at these two data sets, it's kind of intuitively clear that the way to explain this behavior is to say that right at this interface, there is some additional charge. In one case, this charge stabilizes polarization, and then we have this red curve. And in another case, it destabilizes polarization, kind of pulls the dipole towards itself, and we can directly visualize this space charge layer by the observation of the atomic positions. So this is actually super cool. At that time, and at this time, we are kind of stuck at this particular point. We can observe this phenomenon, but there is no other way for us to quantify what goes on there. But the fact that we observe this type of polarization dynamics on the atomic level, it's like literally looking at the fields and polarization fields within the interface as one atom at the time. So it turns out that sometimes we can learn even more complex things. So for example, in the ferroelectric or generally ferroelastic systems, there is a phenomenon called the morphotropic phase boundaries. So the way that it looks is like this. Imagine that you have material like bismuth ferrite. So bismuth ferrite, if it is pure, it is a rhombohedral ferroelectric. So it's R3C. If you dope it by samarium for, let's say, 20%, it becomes paraelectric and orthorhombic, so it is ×2 ordering. So in other words, instead of having the polarization and the unit cell have only one, so the lattice have just, elementary lattice is just one unit cell, you kind of have the antisymmetric period doubling. But the interesting thing is that the R3C phase and the PNMA phase are not crystallographically compatible. They cannot coexist in the same region. What happens in these cases is a very unusual type of the phase boundary in the material, which is called the morphotropic phase boundary. And generally, at this morphotropic phase boundary, if you do the high resolution X-ray scattering data or neutron scattering, you will start to see the signatures of the ordering something like ×4, sometimes ×6, but practically nobody knows what it is. And the great thing about the electron microscopy is that if you look at this type of samples under the microscope, you can immediately see that something interesting goes on, right? You can see that there is some sort of funny contrast inside these images. So if you analyze this data and map polarization and the atomic displacement, you start to see that somehow there are regions when there are no displacements, so it's like almost ideal regions where there are no distortions on the level of unit cells. And in some locations, all of a sudden, you start to have these periodic patterns oriented in arbitrary direction. Again, scattering methods are not going to detect this because these patterns form like, imagine like you have a uniform region, and then these patterns start to form in different locations in more or less disordered fashion. So microscopy can resolve them because they are localized, but for scattering, since their relative positions are random, you will not be able to see them anymore. Again, the question always becomes, where does it come from and what it means? And in this case, the idea is that you need to look at how the different order parameters interact. So for example, if the material has structural distortion and polarization distortion, that means that you have, let's say for simplicity, positive and negative states for polarization, and you have positive and negative state for the structurally distorted material. So if you are in the polar phase, then this one and this one are realized, and this one and these ones are not. But if you have the situation when you're at the domain wall, so the polarization is 0, then the material can have a secondary instability and form the structurally distorted phases. So if the polarization is forced to be 0 by the topological defect, the second order parameter can give rise for the structural fluctuations. And if you spend sufficient amount of time and effort, you can even build the mesoscopic model that explains what goes on, at least qualitatively, and give something which is consistent to the experiment. Now, I mentioned that we also have to deal with the effects of the oxygen stoichiometry. So the great thing about many of this material system is that oxygen cannot be observed directly, so we can see the columns, but if the column is missing 5% of the oxygen atoms, we will not be able to see that. It's not enough change in the contrast. At the same time, if we remove 5% of the oxygen atom, the unit cell will expand by more than 1%, and that's something that we can see very, very well. So it turns out that we can simply measure in materials like lanthanum, strontium, cobaltate, so a very popular material for the fuel cells and spintronics and so on. In this material, we can simply measure the distance between the columns and directly correlate it to the oxygen concentration. The great thing about the electron microscopy is that you can do this type of measurements locally. So for things like films, we would be able to see how the oxygen concentration changes away from the unit cell. And in many cases like this, basically understanding what happens inside the material based on the electron microscopy data pretty much becomes a detective story. Because if I look at something like the interface between the ferroelectric material and the non-ferroelectric material, I can start to measure things like lattice parameter in C direction. So this one is something related to the ferroelectric state and the oxygen concentration. Lattice parameter parallel to the interface. So that one I expect to be clamped, but I still can measure it. I can measure tilts. I can measure polarization from the displacement of the central atom, and I can learn things from yields to some extent, something about the oxygen concentration. And once we look at the data, we can get something like this. So for example, this is the C lattice parameter. So you see some interesting wave here. This is the oxygen tilts. So you can see that in this material, you can see a checkerboard pattern, and here there are no tilts. And you can kind of quantify the positive and negative tilts. And we can even visualize the out-of-plane lattice parameter and see some sort of interesting features. So they're pretty noisy, but they're real and they're there. So it turns out that in many cases, it's very not straightforward to find out what it is. But if you put all the elements together, you can reconstruct the charge of the interface and the strength of the coupling between these materials. And more importantly, we can even discover pretty cool physical mechanisms. So for example, in this case, what happens, this is LSMO, so our substrate. This is bismuth ferrite with polarization in one orientation. This is bismuth ferrite with the polarization in the opposite direction. So technically, polarization comes with a charge. So if we have polarization going this way, then there should be something at the interface that will compensate it. So in this case, it should be negative. In this case, it should be positive. So typically, we think that these materials are sufficiently electronically conductive. So lanthanum strontium manganite is a pretty good electronic conductor. However, what we see is that in this case, we don't see any kind of anomaly at the interface. So in this case, the screening of the polarization charge is indeed done by the electrons. But in this case, you can see that there is an expansion of the lattice parameter close to the interface, which basically, after you go through about a month or two of thinking, basically this means that we don't have the polarization screened by holes, we have the polarization screened by oxygen vacancies. So somehow, the switching of the polarization, we really don't want to have a hole accumulation, we want the oxygen being kicked out and compensate for the polarization charge. And these things matter a lot because people think about this type of materials as the materials for memories, information storage, and so on and so forth. For all of this application, it matters how fast they can switch. And for switching, for speed of switching, the screening matters because electrons and holes can come fast. Oxygen moves relatively slow. So if we need oxygen to move, that means the switching process would be slower, and therefore our material is not very good for application. Second problem is that if we want to switch polarization, we want to switch it many, many billions of times. That's the number of cycles that our memory cell should undergo. If our switching is purely polarization and electrons, we expect that we can do it forever without any damage. If we force oxygen to go forward and backward, sooner or later, oxygen motion will start to destroy our lattice. That's called fatigue. So basically, this type of things, by itself, they all start as something, hey, this is curious, I see something unusual, and that makes me think that this is the right physical mechanism. But practically, once you take this knowledge and put it in the context of what people know about these device structures and their functionalities, that actually answers quite a significant number of questions about why some things work and some things don't work. So what else can we do? So a very important thing in the physics of the ferroelectric materials or generally ordered systems is what is called the topological defects. And to start with a little bit of the background for those, there are two types of phase transitions in the materials. So one is what is called the second order phase transition. So for high temperature, you have symmetric phase, and then the material continuously goes in the low symmetry phase. And practically this happens if your free energy looks like this. There is a second order term and fourth order term. So for high temperature, you have one minimum, and for low temperature, you have two minimum. So the second type of the phase transition is the first order phase transition. So here, if you start from the high temperature phase, At some temperature, you have a jump. In this case, the free energy has second, fourth order, and sixth order term. So basically, you start from one minimum, and then you kind of spontaneously, not smoothly form to minima, but kind of form to minima, and then the whole system kind of drops into those. So it turns out that depending on the type of the phase transition in the system, you can have different behavior of the topological defects. So imagine that you have polarization in one direction and polarization in the different direction. So there has to be a wall between this type of, between these regions. So the interesting thing is that how the polarization at the wall will behave. So in some cases, it can maintain the orientation, but just become smaller and then start to kind of switch the direction. So this is called the block wall. So then you can have the situation when your polarization vector will kind of rotate like this across the direction. And then the third one, when it will start to rotate, this one is Ising wall, this one is the block wall, and this one is the nail wall when it kind of does like this. But there are only three ways how it can behave, either stay in the same plane, or rotate in perpendicular to the wall normal, or rotate into the wall normal. So it turns out that, again, with the electron microscopy, we can actually explore the structure of these walls on the atomic level, atom by atom, and based on that, figure out what is the form of the order parameter in our system. So this is the kind of the more recent example when we take the image. So notice that the image is, of course, imperfect. So these are the defects that formed as the result of the FIB preparation. Interestingly, they don't affect the polarization analysis. So if we find all the atoms in this image and calculate the polarization fields, you start to see the image like this. So this image and this image is the same. You just visualize the polarizations. You can see that some of the domain walls are very nice and sharp, and some of them are kind of much more diffuse. So if it is diffuse, that probably means that the wall is not aligned parallel to the beam. It's kind of tilted in the beam plane. And it turns out that depending on what form of the order parameter we have, the wall will have a simple geometry. For example, for standard material like this one, the wall profile will simply be the hyperbolic arctangent. If we have the order parameter like this corresponding to the first order phase transition, then the domain wall profile would be much more complicated. So it will go like this. It will sort of go through the zero, but close to the zero, it will form the inflection point. And basically, this inflection point means that the material is almost stabilized in the paraelectric state. It's kind of forced to polarization up on the left, polarization down on the right. But as the result in the center, it really wants to form the paraelectric region when there is no polarization distortion. And finally, if we have the system when we have several order parameters, then the domain wall corresponding to one order parameter can lead to the emergence of the secondary order parameter. So simply because you stabilize the phase that is unstable in the bulk, but would be stabilized when the order parameter is quenched. So it turns out that if we take the electron microscopy data, we are actually able to extract this numerical characteristics, and based on that, figure out what type of the order parameter in the system we have. So why does it matter? It matters because, among other things, for macroscopic objects, we, of course, can do these measurements using the X-ray. But to do electron microscopy data sets, we need literally 10 nanometers of the material. To do macroscopic measurements, we need sort of micrograms, many, many billions times more. And interestingly, once we start to experiment with this type of concept, we can also ask more subtle questions, which is what type of microscope do we need in order to perform this type of measurements? So microscopes have certain resolution limits. Microscopes have the certain noise level. And if we do this type of analysis carefully, we can actually estimate what level of microscopy do we need to observe certain physical phenomena. And again, that's kind of important because you may have access to one instrument in your facility locally. You can have access to another level of microscopy if you work with GERD. You can have a third level if you have collaborators somewhere in Ruska Institute. So it turns out that if we understand how our microscope works and how well we understand the physics of our system, we would be able to figure out whether the tool that we have access to can give us the answers that we're interested in. And we would be able to figure out what tools do we need access to in order to get an answer. There are some very interesting things there. For example, a very big role in analysis of the physical data is played by the prior knowledge. So remember the principle that you may have heard many, many times, that the data speaks for itself, right? So this is fundamentally wrong. So don't ever do that. Data has meaning only in the context. Data does not have meaning outside of the context. And the context is our belief about the system. So it turns out that if we don't know much about the system, so let's assume that the red region is the region where we can learn something interesting. The white and blue region is the region when we cannot learn something much. So this is the region of in terms of resolution and noise, where we can learn the physics of the material based on the observations. So if our prior knowledge about the material is fairly unusual, fairly uncertain, this region is relatively small. If we introduce the physical constraints, so we say that we know something about the basic physics reasonably well, this red region becomes larger. So that basically means that we can compensate for the lower resolution of the instrument by adding some prior knowledge. But interestingly enough, if our prior knowledge is incorrect, so we are confident about the wrong facts, then unfortunately there is not much we can do. So it's much better to be skeptical than optimistic. So what else can we do? So interestingly, similar type of analysis can be applied not only for polarization, but also for more complex things like vacancy ordering. For example, in materials like cobaltites, they really vacancies really like to order and form the Brown-Millerite plane, so you see these periodic patterns. So if you have periodic patterns starting at a different part of the sample, they can be misaligned. So this is called the antiphase boundary. So if you visualize this antiphase boundary, you can basically reconstruct the effective screening lengths and basically match it to the solution of the same type of Ginzburg-Landau equations. And the same type of approaches work for, again, more complex orientation. For example, if we talk about the ferroelectric vortices, then vortex has a shape which is determined by what is called flex-electric coupling. So flex-electric coupling is very difficult to measure macroscopically because it manifests only on the atomic scales. Basically, what it is the coupling between the polarization and strain. So it's a very subtle effect. And in macroscopic objects, we cannot create large strain gradients because they will just form apart. But on the nanoscale, strain gradients can be fairly large. So it turns out that, so what we want to do is we want to somehow get the numbers, the value of this flex electric tensor. So it turns out that if we have the electron microscopy observation of the vortices, then we can do the phase field simulation of the vortices, and the shape of the vortex would be very much dependent on the magnitude of the flex electric effect. So if the flex electric effect is small, the vortex will look almost like square. If the flex electric effect becomes larger, then it starts to look like a ninja throwing star. And if the flex electric tensor is very large, then there will be a secondary instability and the vortex falls apart into much smaller vortices. But if the shape of the vortex depends on the strength of the flex electric coupling, that means that we can take experimental data and find the best match between the theory and experiment, and the best match will tell us what is the value of this flexoelectric coupling coefficient. So this is kind of an example when we have a complex atomically resolved data set. We have a theoretical model with relatively simple low-dimensional parameter space, and we find in which part of this parameter space the match between experiment and theory is the best. And that in turn tells us what is the value of parameter that we would not be able to get in any other way. So what else can we do? So one of the very important things in science is the matter of complexity. So for example, imagine that you look at the snapshots of the ideal solid solution, right? So this is just a random distributions of atoms. So the distribution themselves, the number of possible clusters, the geometries would be very, very large. But despite the fact that the number of possible atomic configuration is large, the rules behind these combinations are very straightforward. There is a very simple model that basically tells us that atoms don't care what their neighbors are. So that's a very important thing, because very often our observations are complicated, but the rules of the model that gives rise to this observation would be very, very simple. So in some sense, when we remember that in the opening lecture, I said that we always should go for physics rather than data. So trying to understand all the possible configurations of atoms in the ideal solid solution is kind of complicated. There are a lot of them. It's kind of very complicated correlative model. But if we try to understand the rules that govern the dynamic of the atoms, the rules would be very simple, except that we observe the atomic configurations and we don't observe the rules. So one of the tasks for microscopy is essentially do the same type of things as the astronomers. Astronomers observe how the planets move and they learn the laws of how the gravitation, they interact through gravitation or whatever. So what we want to do with the microscopy data is observe how the atoms are distributed and try to get an idea of what are the interactions between the atoms. So that's actually kind of a common problem in the condensed matter physics, because one of the basic instruments of condensed matter physics is what's called the microscopic models, like Ising, Heisenberg, Kitaev, and so on. So these are the lattice models. So physicists love to kind of formalize them and calculate them. But typically, once you do the numerical simulation, that will give you something like macroscopic observables, like properties, average structure, fluctuation spectra, and so on. And then if you have the real material, you study it by microscopic measurements, and then you somehow try to compare macroscopic observables to macroscopic measurements, and from that you want to infer the microscopic behaviors. So this is how condensed matter physics worked for the last 80 years or so, and it worked very successful. But the direct question is, do we actually have to do that? So what if we observe this microscopic degrees of freedom directly? Can we learn the microscopic laws directly from this microscopic degrees of freedom? So interestingly, this story is less than 10 years old, because even trying to connect the microscopic models to macroscopic observables through machine learning, this was a paper less than 10 years ago, even though it sort of sounds like it was eternity. And I can give this type of problems as the homeworks in my class just because now it's doable. So let me show you an example. So simplest example of this type of models is the Ising model. So it's basically the lattice that have spins on it. Spins can be up and down, and there is some energy with which the spins interact with each other. So the natural question is, can we take the real material data and find the single parameter of how strongly the spins interact? So it turns out that it's possible. So imagine that I take the material, which is the molybdenum sulfide doped by rhenium sulfide. So rhenium is much heavier. So if you have 5% dopant, you can see that there are bright rhenium atoms, right? So notice what happens if I start to increase the amount of rhenium. So I can see many more bright atoms, right? And The second thing that goes on is that the symmetry of the lattice start to change. So this one is very clearly symmetric, and this one very clearly form this periodic structure, right? So you can see it. And of course, it's very easy to analyze because, for example, if I calculate the pair distribution function, you can see that here the neighborhood is almost ideal, low noise and no distortion. Here you can see that there are peaks start to broader split, and here peaks have split, but they become narrow. So the disorder is lower, but there is a symmetry lowering transition. So it turns out that for systems like this, we can do the direct mapping between this Ising model and the images that we observe in electron microscopy. So how exactly we do that? This comes with a little bit of technical details. So the question is, what do you use for comparison? So practically, it turns out that the correct way to do that is through the histogram of the possible atomic configurations. So basically, you calculate the possible histogram of possible neighbors in the model and in the experimental data, and then you try to find out in which part of the parameter space the distance between the histograms is smallest. So, and there are kind of good reasons why this is correct metrics and other metrics is not. But this is what you get as the result. So if you say that the interaction between atoms is determined by either model like this, so pairwise additive, or by many-body model, you can see that if we plot our energy surface, error surface, then if the particles were non-interacting, this is clearly not the minimum. So particles are interacting. If we consider only nearest neighbor interaction, we will be somewhere here. So better, but still not perfect. But if we consider nearest neighbor and nearest neighbor interactions, then we actually at the minimum of the surface, and we kind of get the idea that the rhenium atoms kind of mildly push away from each other. So compared to the ideal solid solution, they try to be sort of further away from each other, kind of it's like a weak repulsion. And with the many-body model, we basically have roughly the same answer. So why does it matter? It matters because we looked at the material. We know that the statistical observations don't generalize. If we observe material for 5% concentration and 10% concentration, we cannot figure out based on statistics what would be at 7%. Also, we know that the observations like this do not allow us to extrapolate to different temperature. Because if we do measurements at one temperature and we don't have a model, we cannot extrapolate to a different temperature. But if we learn the model of atoms interaction, then we can extrapolate to all concentrations and all temperatures. So we learn the generalizable model. I mean, admittedly, in this case, our error bars are large, so the quality of this interpolation would be not particularly good, but the fact that it's possible by itself is already very, very non-trivial. And then we can do even more interesting things. So remember that when we talked about the polarization mapping, we said that we observe the positions of the atoms and we see how the atoms shift by the high symmetry position, right? And then if we map it for all atoms in the field of view, we get our order parameter field. So when we deal with the disorder system like this, we basically have, if we look at it on the global level, we have one average concentration, right? But if we look at it locally, we deal with the small clusters with different concentrations. So just statistically, one place will have more rhenium atoms, another place will have less rhenium atoms, and so on and so forth. So globally, it is the same material. But locally, this is the combination or mixture of the regions with the different concentrations. So for example, if I look at the part of the lattice that has 7 atoms, kind of central atom and its nearest neighbors, then if I take a 5% rhenium concentration, then most of the clusters will have 0 rhenium atoms. Some will have 1 rhenium atom, and very small will have 2 rhenium atom. If I take the, let's say, 55% rhenium concentration, then I will have multiple clusters having 1, 2, 3, 4, and so on rhenium atoms, just statistically. And what turns out is that if I measure both the local rhenium atom concentration and the distortion of the lattice, I can basically plot how much the distortion depends on the local concentration. And this is absolutely amazing because basically you can see that this type of distortion mode does not depend on concentration. And this type of distortion mode kind of doesn't depend on concentration. And this type of symmetry breaking mode, it's kind of constant for low rhenium concentration, and then it starts to open up. So basically this phase transition, when we have the symmetry lowering transition, we essentially can observe it on the atomic level if we analyze the statistics of our atoms well enough. So that's the value proposition of the electron microscopy if done well. Now, there is this general principle that if you do some work well, then what do you think is the reward? Guys from my group, you should know that. Okay, so if you do your work well, that means that you get more work, right? That's the only way it works. We should discuss how comes that's not a common knowledge. But in this case, if you do it in physics, if we do the work well, we start to get access to the fundamentally new opportunities to learn something. And for example, when we talk about this type of materials, we know that when we change molybdenum by rhenium, we do two things. So first of all, we change the effective size of the atom, so that's a chemical effect. And secondly, we change the number of electrons in the system. So if we change the number of electrons in the system, that can introduce the symmetry breaking just because the position of the Fermi level changes. And if we change the size of the atom, that also can introduce the symmetry breaking because of steric effects. So the question becomes, how can we separate them? So in the classical physical approach, this can be done using so-called field effect. So if you make a material in the form of the transistor and you apply gate voltage, you can change the number of electrons without changing the chemical composition. The problem is that we cannot run this type of experiment in the electron microscope. But what we can do is there are ways to analyze the data that allow us to build the causal rather than correlative relationship between the properties. So that's a very interesting direction. It's possible to do it when we have a lot of observations, and observations are precise. And that's kind of one of the areas that electron microscopy has opened, but has not been explored until this moment. So something to keep in mind for the future. So let's stop here. And so I hope I gave you some idea about how we can learn physics. So the logic is that we observe materials, we map the atomic positions, then we return then we use this atomic position to calculate the local analogs of the physical order parameter fields that people know how to work with. And then we feed them either to mesoscale models or to the lattice models. And at this point, let's switch to the hackathon. Okay, questions are good. Probably, I don't know. I mean, there is always a convolution with the probe state, but that's pretty much the primary mechanism. Sure.
I've studied ITC materials.
So ITC, like YBCO?
Yeah.
I mean, we worked with the Amit Gayal group on kind of exploring what happens there. But yeah, you can learn quite a lot about these materials, especially under the radiation damage, because you have oxygen information, you have the kind of the buckling of the copper layers and so on and so forth. So these are pretty cool.
Transmission temperature on the order parameter, nature of the order parameter, how it form that what they are on.
So that one is complicated because from electron microscopy measurements at room temperature, we can get structure, right? So if we get structure, we can postulate that there is some relationship between structure and TC, but that would be a postulate based on macroscopic physics. It's not measurable. If we somehow could measure the local structure and local superconductive order parameter, that would be a kind of Nobel level type of experiment. But until we know how to extract the signatures of local TC from eels, we cannot do that. So it's kind of an area where we're getting close because it's intuitively clear that if we start to analyze the high resolution eels to the limit, we should be able to learn things like quasi-particles, the kind of behavior, superconductive gaps, and so on and so forth. And that indeed would be the ultimate experiment. So being able to measure the quasi-particles and electronic structure from eels and correlate it with the structural signatures, that would be absolutely amazing.
For practical question, the T direction, what's the range of the T direction you can?
So with the modern, Gerd can correct me, but with the modern methods, if you do the focal series or tachographic reconstruction, we can get something like 3 to 5 nanometers in Z. So that's your, if you do reconstructions well, your probing volume would be localized in terms of information limit, something like a picometer in the XY. So the true resolution is of course much worse, but position sensitivity can be made as small as a picometer. But in the Z direction, it would be kind of like an ellipsoid, which would be a order of 3 to 5 nanometers.
You're talking about optical resolution in the
It's not resolution, it's a position, it's how well you can position the center of the cation column. So the resolution would be much lower, but just imagine that you have a shape like this, right? So you can, if your noise level is low, you can localize the maximum much more precisely than the width of the whole feature. It is possible to see the thermal broadening. So by now, again, with the tachographic reconstruction, we can observe, we can reconstruct images where the size of the atomic features would be thermal broadening. That being said, we see the thermal broadening, but we can determine the center of the ellipsoid much more precisely than the size of the ellipsoid. It's a kind of subtle difference between resolution and information limit. So information limit basically is determined by, resolution limit is limited by imaging system. Information limit is basically is determined by the interplay between resolution and noise. In some sense, if our noise is 0 and our accumulation time is infinite, our positioning sensitivity can be almost kind of very, very precise.